Welcome to the lecture series on mathematical modeling, analysis and applications. In the last lecture, we have discussed this single species population model, and based on that we have just discussed this intrinsic growth rate of the population. And in the last phase we have discussed this Ali effect. Ali effect, especially this depends on special class of population modeling, and that convergence analysis we have also discussed thereof. And in the present lecture we will just go for this discussion of phase diagram here. So, first we will just discuss here what is phase diagram is, then the different class of phase diagrams. This means that in one dimensional ordinary differential equation how we can just do this phase diagram analysis, that we will just discuss. Then we will just go for this phase diagram analysis for 2D uncoupled system, then we will just go for coupled system here. And especially if you will just see here, for uncoupled system it is very easy to do this analysis in a graphical sense, but in case of coupled analysis we can just find lots of troubles and difficulties which can be handled by using different techniques. So, first if you will just go for this introduction to phase diagram here, that especially why we are just going for this phase diagram is that when we are just seeing that the stability of a differential equation we are just finding, and it is very difficult to find the stability analysis in case of first order differential equation or second order differential equation, then we cannot comment also anything by looking at the nature of the graph about the steady states. So, especially whenever we are analyzing any population dynamics model, first we are just finding the steady state population level, and this steady state population level depends on the first order differentiation, it should equals to 0 there. And especially if we are just getting some points at that point, whether it may just provide a steady state or whether it is just providing a a stable solution or a unstable solution, that we cannot predict it out. Also, for the system of a differential equation we are calculating the Jacobians about steady states, and then depending on the sign of calculated eigenvalues we are concluding the remark of the stability. But especially it is difficult to find this Jacobian matrix, or when we are just calculating the eigenvalues, and we cannot say that what type of behavior especially it can just shown whenever we are just going for stability condition or instability conditions. But do you think that it can be always be easy to either solve differential equation or calculating eigenvalues from Jacobian matrix? Especially no, it is not easy always. So, as the complexity of a differential equation increases, many times it is not even possible to find the solution. So, especially if you can just remember this Kobe graphs and the numerical solution to find this eigenvalues for discrete time models. So, it is very difficult to find this eigenvalues, also to find the solution in Kobe of graphs there. So, if we cannot handle complex differential equations in easy form to find this stable conditions or unstable conditions at the steady states, then it is easy or it is difficult to go for some solution process where we can just find the solutions in complete form. So, for that we are just going for this phase diagrams here, and for the phase diagrams especially we can proceed with the two methods. So, whenever we are just finding these difficulties, first is the numerical solution of a differential equations, then the graphical solution of a differential equations. And if we are just discussing only the graphical solutions, the graphical method which we are just going to discuss is known as phase diagrams here. Especially if you will just see that the solution process we have discussed also this graphical solutions in co-wave graphs also there, but that is for steady state solutions, not to check stability or instability conditions. But here if we are just proceeding towards the numerical solution of any differential equations which is just representing this your population balance modeling, then we have to first start a scratch analysis of the solution in a graphical form. And this is nothing but the phase diagrams especially it is said to be. The graphical method which we are going to discuss is known as phase diagrams, also called phase portraits here. In layman terms, as I have explained, that phase diagrams are similar to the painting or cartoon sketch of an image. obviously if we can just see this like when some thefts has been occurred. So, if somebody has seen his figure, then the sketch artist has been like called and they are asked to what is its like fundamental sketch of his figure. So, then this like eyewitness, he is just providing the idea that you can just put his hairstyle this one and face style there and eyes are there. So, based on that the sketch artist just put a like graphical abstract that how he can looks to be. The same analysis we will just do for this phase diagram here. So, a painting or sketch gives us only the lump sum idea about the characters or the objects in it, but not give us the complete clear vision of the same. Similarly, phase diagram of a differential equation provides us certain information to study the stability, but not gives the complete solution here. This means that obviously if we are just plotting this abstract solution of any differential equation in a graphical sense, so completely it can just provide this physical behavior, how it is just performing in the system, not the complete scenario point to point where it has a change is occurring or where this like variation is coming, that we cannot predict it out. Hence, instead of finding the exact solutions, if you suppose it is difficult to find the exact solution in case of a numerical solution or in analytical approaches, we can just visualize the things from the graphical sense, and we can analyze the differential equations qualitatively. And that is why these phase diagrams are qualitative approach to solve the differential equation. So, obviously it is not providing the exact solution of the differential equation, and we are just visualizing this system in a like a graphical sense here. So, that is why we can just say that it is just a approximated solution of the system, and approximated solution especially it can be just provide us a qualitative idea that how the solution behaves or performs there. So, that is why these phase diagrams are qualitative approach to solve the differential equations. We are just estimating that in that form. Let us assume a system of the matrix. Suppose if we are just going for this phase diagram here, first we are just considering a first order linear equation here, that is in the form of dx by dt equals to ax. And if it is a like a system of equations, then x is a vector of length n here and A is a square matrix of size n. And then this phase diagram or the phase portrait of the system of a differential equation represented by dx by dt equals to x is the set of all solution curves in the phase space R to the power n. Since we will have like n variables are involved with this equation, or we will have like n set of equations, then it can just provide this graphs in a n dimensional space there. Especially we are just considering the real space. So, that is why we are just writing here R to the power n. So, if you just go for a simple analysis of one dimensional ordinary differential equation, consider a differential equation that is in the form of x dash equals to cos x. I can just write this one as a dx by dt equals to cos x suppose. And if we will just find the solution of this differential equation using variable separation method, we can just write this one as a dx by cos x this equals to dt. And if you just integrate both the sides, then we can just write ln of sec x plus tan x this equals to t plus ln of c here suppose, or ln of k I can just write. And if you will just try to find the solution for the system here, so ln of it can be written as 1 by cos x here plus sin x by cos x, which can be written as a t plus ln k here. And if you will just go for like further manipulation of the things, then we can just write this one as 1 plus sin x by cos x, which can be written as a t plus ln k here. And then if we will just go for the further analysis of these things, then we can just write this one as ln of it can be written as a sin x by 2 plus cos x by 2 square by cos x. So, cos x can be written as like I can just write cos square x by 2 minus sin square x by 2 here. And if you will just cancel it out to both these terms in the numerator and denominator, then we can just find this is as like ln of tan of pi by 4 plus x by 2, which can be written as a t plus ln k there, and the final solution you can just obtain as like tan of pi by 4 plus x by 2, this is equals to k e to the power t here. Since I have not done the complete calculation here, since the space is less here, but obviously you can just do this one, since if you just cancel it out one term here, sin x by 2 plus cos x by 2 by cos x by 2 minus sin x by 2, it will be there. So, if you just take common of cos x by 2, then it will just give you this tan form there, and obviously it can be written as like tan pi by 4 plus x by 2, where k is a constant here. And the steady states of this differential equation of this equation, if you will just see, since steady states are achieved whenever we are just writing x dash equals to 0. So, this means that cos x equals to 0 we are just putting here. So, if cos x equals to 0, that is nothing but x equals to n pi plus pi by 2 here for any integer n here. And if you will just analyze this plot in a graphical sense here, you can just see that alternate steady states are stable here. For example, the solution starting near pi by 2 means this is just coming here, we will approach to pi by 2 only. If you will just perturb close to its neighborhood values, then obviously it will just come to that values. And obviously if you will just see here, when we are just starting this values near minus pi by 2 also here, then suddenly this graph is approaching towards pi by 2 here also. Hence, we can just say that pi by 2 is the stable steady state, which is just representing a stable steady state here, and minus pi by 2 is unstable. Since whenever we are just perturbing any values close to minus pi by 2, it is not going to minus pi by 2 there, it is just tending towards pi by 2 here. So, that is why we are just considering here minus pi by 2 is a unstable state here, and this can be achieved if you will just go further also like 3 pi by 2, then this value is also going towards the next immediate cyclic value there. So, similar way we can just find like negative values, and then we are just find that this periodically it is just providing a stability with respect to the other values here. And this is especially we are just analyzing in a one dimensional sense here, and if you will just go for like further analysis of this phase diagrams in one dimensional sense here, even if you do not know what it will just behave inside the system, and from the like function itself, if you will just plot this graph here, suppose cos x graphs, if you just plot here, then we can just see that x dash t is nothing but it is just represented in the form of f of x, which is just written as cos x here, and this is nothing but the graph of cos x. And we call a point as steady state, since at that point we are just assuming that x dash t equals to 0. Hence, the intersection of these points of phase diagram with the x axis, it is just giving you the steady states here. Since especially we are just finding here x dash equals to f of x, this equals to cos x, and wherever cos x is 0, that is nothing but the points of steady states. And especially from this graph you can just find that A and B and C are 3 points where this cos x intersects with the x axis, and which is providing the steady state values. Now, if you will just perturb the values in the neighborhood of a point A, suppose, so any close neighborhood points if you will just consider on the left of point A, we can just find that x dash greater than 0 here. Since x will increase and come towards the point A here, and if you will just start from the right here, we can just find that since x dash is less than 0 here, if you will just see, and at this level you are just finding this is positive values. Hence, x will decrease and come towards the point A here. If we will apply any perturbation to steady state A here, it will come back to point A only, hence it is stable. So, that is why we have just written here, if you will just perturb any values in the neighborhood of A, since x dash is greater than 0 on the left part of A here, since it is positive here, and it will just increase and come towards, since it is increasing in this direction, so it will just come towards the point A here. And if you just see this right hand side here, then you can just find that this is monotonically decreasing, since this represents here negative values, and this will just decrease afterwards. So, that is why it will just approach towards the point A here. So, which is represented by red arrows for this figure. And if you just go for further analysis of all other points here, you can just find that for the point B here, you can just find that this left hand side, it is monotonically increasing. Increasing means it will just move further outwards. And if you just see here, this right hand side, this is negative values, it will just move further to the rightwards there. So, that is why it will just move in this direction, this will just move in this direction here. So, that is why both these points will move far away from that point B. So, that is why B is a unstable point here. And if you just point C here, then the left part, if you just see here, left part means this is like a monotonic increasing function here. Monotonic increasing function means afterwards it will also increase, then it will just move towards the point C here. And if you just see the right portion here, then right portion it is monotonically decreasing. So, it will just decrease again, then it will just come towards the point C. So, that is why we are just saying C is a stable point here and A is a stable point here, but B is an unstable point. Since the points, if you are just pointing here, then this is like monotonically increasing means it is going far away, and monotonically decreasing means it is also going far away. So, this is especially called phase diagram of x equals to cos x here. So, that it is written here with similar arguments, we can show that steady state point B is unstable while point C is stable. Now, if you will just observe the slope near this point, so have you find anything interesting? If you just see the slopes here, especially the positive slopes, especially this just moves like this one. If you just see here, or if you just plot the slopes here, and if you just plot the slopes here, and if you just plot the slopes here. So, especially these slopes are like especially it is called negative slopes, and especially this is called positive slopes here. Since you know that the function, whenever we are just putting the slopes like y equals to x, so then it is just representing the positive slope. If you just find the trend, we are just saying here. So, if you just see here, the slope of f x equals to cos x, f dash x at point A and C are negative, especially if you just see this is negative slopes. But at the point B, you can just find that this represents a positive slope there. So, hence it represents if it is in a steady state, and especially we can just say that when the slopes are positive, then we are just finding this points are unstable, and if the slopes are like negative, then the point represents the stable state there. So, that we have just written it off here in a complete sense. The slope of f of x, f dash x at point A and C are negative and they are stable, while f dash x is positive at point B, and it is like unstable here. So, in general, if x 0 is any steady state, that is f of x 0 equals to 0, then x 0 is a stable steady state if f dash x 0 is less than 0, and unstable if f dash x 0 is greater than 0. So, we can just compare these solutions with exponential solution of differential equations, especially if you just find like any differential equation also. So, the solutions are represented in the form of like x 0 equals to e to the power like lambda values if you just write. So, it will be written as e to the power minus lambda t. So, if lambda is negative, you are just saying it is like representing a stable solution, and whenever lambda is positive, then you are just saying it is a like unstable solution. This means that if you just take this difference differential of these equations, suppose if you can just represent the solution in the form of like x as e to the power 2t suppose, and another solution suppose x equals to minus 3t. Then if you just take the differences here like dx by dt, you can just find that this is 2 e to the power 2t, and dx by dt this is like minus 3 e to the power minus 3t minus 3. So, you can just find that this represents the negative slope here, this represents the positive slope. In case of positive slopes, you are just finding the system is unstable, and in case of negative slopes, you are just finding that the system is stable there. So, that we want to say, that is why we have just written that compare with the exponential solution of differential equations. So, if you will just go for a phase diagram analysis of a logistic growth function here, consider the logistic growth function. Suppose especially we have discussed these equations in the earlier lectures, that is in the form of n dash t equals to k n of t C 0 minus alpha n of t, where C is nothing but this like concentration or this food or like the supply of the concentration, it should be provided there, and this n is represents the population growth level there or the population size n of t, and k is the rate of this population growth level or decline, it can just be controlled. Then this steady states for this equation, that it can be represented in the form of n dash t equals to 0. So, steady state means especially first order difference equals to 0, we are just considering. If you will just consider n dash t equals to 0 here, then we can just consider either n equals to 0 or n can be taken as like C 0 by alpha from this equation. And if you will just see here, this means that to find like the nature of the stability for this function here. So, we have to like perturb the value around the steady state values. So, if you will just plot in a graph here, we can just find that n equals to 0, suppose it is placed here, and n equals to C 0 by alpha at this point. Then at n equals to 0, if you will just perturb any value, then we can just find that in the right hand side it is monotonically increasing function. So, this will just go on increasing and it will not tend towards the point n equals to 0. And if you just see the right hand side here, this is a monotonic decreasing function. So, that is why it will just go further outwards. So, that is why we can just say that n equals to 0 is a unstable point here. And if you just go towards the point C 0 by alpha here, and if you just see the right hand side here, then this function is monotonically decreasing, then again further it will just decrease towards the point C 0 by alpha here. Hence, we can just say that this is a stable point here and this is a unstable point, and that we have just written also. If you just put the slopes also here, then you can just find that this represents a positive slope here and this represents a negative slope here. And especially from the last slide, we have just concluded that when this slope is negative, then we are just saying the point is stable, and when the slope is positive, then we will have a unstable point there. So, that you can just verify yourself. So, then we have just written that one in a like phrase here. By perturbing the values near n equals to C 0 by alpha, they will approach back to the same point, and hence it is a stable steady state. So, you can just verify by considering like the slope should be negative there. And this phase diagram analysis, if you just consider for Ali effect model, then for the Ali effect model, we can just find that this equation is represented in the form of dn by dt. This equals to Rn into n by a minus 1 into 1 minus n by k. And if we want to find this steady state here, we can just put here dn by dt equals to 0. This means that you will have like n by n equals to 0 is the first point, then second one is like n by a minus 1, this equals to 0, this implies that n equals to a, and second term if you will just see, third term if you will just see here, then 1 minus n by k, this equals to 0, this implies that n equals to k. So, 3 different points we are just getting for the steady states, n equals to 0, n equals to a, and n equals to k. And from this equation we can just find that n dash t can be written as like f of n here, which can be written. And if you just plot this graph, then we can just find that at these 3 points n equals to 0, n equals to a, and n equals to k, we can just find that f dash n is less than 0. This means that at this point if you just put the slope here, and at this point if you just put the slope here, and at this point if you just put the slope here, then you can just find that at these 2 points we will have negative slopes, and at this point we will have a positive slope here. And especially we can just find that this function behaving like it is just going at outwards from this point when we are just approaching towards this point A here. Since at the left hand side, if you just see here, the point is further monotonically decreasing, and at this level in the right hand side, if you just see, the function is further increasing outwards. So that is why if you just see here that n equals to a represents a unstable point, and n equals to 0 and n equals to k represents a stable steady state here. And if you just go for like further analysis, since both that we have just discussed till now are like one dimensional differential equations. Now if you just go for two dimensional differential equations here. So two dimensional linear difference system, if you just consider here, in the first phase if you just consider a uncoupled system here, consider the same equation, that is dx by dt equals to ax, whatever we have just defined for the equation 17.1. And if we will just consider two linear set of equations in that form, that is suppose x dash equals to x and y dash equals to minus 2y here. Each of this system has only one independent variable, if you will just see here, sorry, one dependent variable, since it is written as dx by dt equals to x here and dy by dt equals to minus 2y here. So x and y are dependent variables, and t is the independent variable. So that is why we have just written each equation of the system has only one dependent variable, x, it is present there. Overall the system has two dependent variables, x and y, and one independent variable. The first equation of the system, if you will just see here, has a dependent variable x, and the second has a like dependent variable y here. And this system, since we have not coupled this system, means x is not involved in the second equation and y is not involved in the first equation, then this type of system is termed as an uncoupled system. If we represent the system in a matrix form here, since we have like a diagonal matrix, we have to form it out. So that is why if you will just write this one in a Jacobian form here, then we can write the first derivative here, that is with respect to x as 1 here, and with respect to y there is no variable. So that is why you have just considered 0 here. Second one, if you will just see, there is no variable x involved in this equation. So that is why 0 it is there. If you will just take the first order differentiation with respect to y, this is just giving you minus 2. So this matrix representation just it is just giving 1 0 0 minus 2 here. And if you will just see, the eigenvalues of this diagonal matrix are the same as that of entries of the diagonal, since already we have known that if it is upper triangular matrix or if it is only diagonal entries are present there, then the diagonal elements are nothing but the eigenvalues. So the eigenvalues of this matrix A is 1 and minus 2, 1 and minus 2, that is nothing but the diagonal entries here. And if you just write the solutions, x of t, that is nothing but c1 e to the power t, y2 equals to c2 e to the power minus 2t. You can observe that this is very easy to get the solutions when the system is uncoupled. Especially if you just directly find the solution, you can also find that is nothing but dx by dt equals to x here. So dx by x, it can be written as dt here. So just integrate this one and you can obtain also the same solution. And if we want to plot this function in a phase diagram, or if we want to find the phase diagram of this same, first we will find a relation between these two dependent variables x and y. By simple algebraic method, we can just find that the relationship as x square into y, this is suppose k. Since we will have a uncoupled system here, x equals to c1 e to the power t and y as c2 e to the power minus 2t, and since if you just see that x is dependent on t here and y is also depending on t here. So, we can just establish this relationship in the form of x and y here. And if you just take like square of this function here, so then it can be written as like c1 e to the power 2 t here. And if you just see here like y equals to c2 e to the power minus 2 t, this means that we can just establish this relationship x square into y. So, it can 2 t and minus 2 t. So, it can be like since c1 is involved as the constant here and c2 is involved the constant here, then obviously if you just take this constant as c1 square and c2 here, then we can just write this is capital K here. And if we will just go for the analysis of this equation here for positive value of K, we can find the upper half portion of this graph. This is shown as in figure 17.5 here. And for negative K, we can just find this lower half of this graph, and the only steady state is achieved at 0 0 level here. And if you just plot out these values, then we can just find that along the x axis, if you just see the values are moving away, but if you just see the y direction, the values are coming towards the origin here. So, x axis means this is just going outwards and y axis means this is just coming towards the origin here. So, if you just analyze this one, that we can just find that if we plot out variable x along x axis, this is nothing but x axis here, then it will move away from 0 0 because of a positive eigenvalue, since 2 eigenvalues we are just obtaining, and for like 1 we are just finding that it is just going away from this origin, and for minus 2 we are just finding that this is coming towards the origin there, and that we have just written. Similarly, if we plot out the variable y along y axis, then it will just come back to the point 0 0 because the negative eigenvalues here. And if we will plot out both these values at a time, then when this minus 2 values like eigenvalue for minus 2, if it is just forcing towards the origin, then this x value which is positive, it is just taking outwards. So, then combinedly it can just represent a unstable condition at the point 0 0. So, this is for the uncoupled system here, and if you just go for like coupled 2D linear system, then we can just find that it is very difficult to handle, since in a uncoupled form we are just obtaining the solutions in a independent form, and we are just trying to establish this relationship within these two variables. And the matrix is diagonal also, it is just coming. So, that is why easily we can also find this eigenvalues in a compact form. But if the system is coupled, in that case the matrix will not be in diagonal form. Thus, it is difficult to calculate the eigenvalues. We have already dealt with the difficulties involved in finding the eigenvalues, since we have discussed like power method and LR method to compute these eigenvalues in the previous lectures. And in that cases, especially like a power method or LR method, since we are considering here only LR method, since after few iterations we try to get it in a diagonal form of the matrices, and once it is in a diagonal form, then we can just predict that the diagonal entries can be the eigenvalues. Physically, it means that we are just transforming an uncoupled system into a coupled system there. This means that final form, if certain iterations we are just doing, or we are just trying to formulate like a coupled matrix which has like all the entries are there into a diagonal transformation form, then we are just trying to find the solution that is in a uncoupled system to a coupled system there, or sorry, if it is like coupled system, then we are just trying to set these equations in a uncoupled form, then we can just represent that one in diagonal form of this entries. So, if there is a coupled linear system, we can find its eigenvalues and then we can plot the phase diagram after getting a mathematical relation between them. And the nature of the phase diagram will be entirely dependent on the eigenvalues. Obviously, if you will just see in 2 dimensional case, this characteristic equation will be of degree 2 there, And so, the possible eigenvalues are like both these eigenvalues will be real or a pair of complex eigenvalues, we can just get it over there. And if we will just go for like theoretical analysis of this 2D linear system for the stability, then we have to find first the eigenvalues. So, let the eigenvalues of a 2D linear system are suppose A and B. So, we are just considering first in the case of like when the eigenvalues are both real here. So, if eigenvalues are both real, in the first case if you are just considering here two eigenvalues are A and B here, and if both the eigenvalues are strictly negative suppose, then we can just say that we will have like asymptotically stable condition, because the solution will converge to a steady state after certain time, or it will just take some time to reach to the steady state. And if one of the eigenvalues is positive, then the system is unstable, because the positive eigenvalue it will just make this system to increase exponentially, and hence it will just get diverged. And if one of the eigenvalues is 0 and one of the eigenvalues is negative, then we can just say that the system is completely stable. And it is not asymptotically stable, since in asymptotically stable sense it just takes some time, or periodically it will just come towards the point of stability there. So, that is why it will just take some time. So, but particularly if one of the eigenvalues is 0 and another one is negative, directly we can just say that it is stable. And in the complex case, if the real part of complex conjugate pair of eigenvalues is negative, then the system is asymptotically stable. So, it will just form the spirals and will converge to the steady state in spiral fashion. And if the real part is positive, then it will obviously it will just diverge in spiral fashion, and hence the system is unstable. And if we will have like 0 real part, it will simply form an ellipse and it will be stable only. Since completely it will just form a ellipse there, and we can just say that the system is just lying in that phase only. So, that is why the system will represent a stable condition. So, if we will just go for like a role of eigenvector in a phase diagram, then in general it may be difficult to find the relation between dependent variables, especially when both these eigenvalues are complex numbers. To avoid this, we will try to use the concept of eigenvector to draw the phase diagram. So, when these eigenvalues are represented in a complete form, then we can just say that we can just go for like analysis of the steady state points, whether it is just represents a like a stable solution or unstable solution. But if it is complex pairs, it is difficult to handle. So, first we will just establish this relationship with the eigenvalues with the eigenvectors, and this vectors representation it will just provide us the idea in the phase diagram that whether this system is stable or not. So, if we want to find this eigenvectors for the system, especially we are just writing this system as in the form of A v equals to lambda v, where v is the vectors here, and each of these eigenvalues we will have a corresponding eigenvector. And since eigenvectors are represented corresponding to each of the eigenvalues, so eigenvectors are not unique. So, in the first sense we can just consider the uncoupled linear system. So, if we will just consider this uncoupled linear system that we have just considered in the example like equation 17.5 here, we will have this diagonal entries is 1 and minus 2, if you can just remember. Yes, 1 and minus 2. And especially we are just writing here this diagonal entries is 1 and minus 2. The eigenvector for lambda equals to 1, if you just consider, since A is the complete system we have just written, and we can just write this one as like A minus lambda into V, this equals to 0 here. So, if you will just subtract this one from this diagonal elements like A minus lambda I, especially we can just write, since A is a matrix here, then obviously we are just writing here A is the system that is in the form of like 1 0 0 minus 2, 1 0 and 0 minus 2 it is just given. Corresponding to lambda equals to 1, you can just find that we will have a vector that is in the form of 1 0, and corresponding to eigenvalue lambda equals to minus 2, you will have a vector 0 1 there. So, this eigenvectors it will be written in the form of like here, that is 1 0 and second one is a 0 1 here. And if you just draw these eigenvectors, so especially, so in the first case you can just find that this is nothing but the x axis here, that is x equals to 1 and y equals to 0. In the second case, if you will just see, this is nothing but x equals to 0 and y equals to 1 here, that is nothing but y axis here. So, if you just draw these eigenvectors here, so the steady state it is just achieved at 0 0, and both these axes, that is x axis and y axis, it represents this vectors there. And if you will just consider any test point on x axis, suppose I am just considering as the point suppose 0.50 suppose, and at this point if you will just see here, so x dash equals to x, so that is nothing but 0.5. So, the slope is positive here, so it will just give a unstable steady state there, and which will just diverge there. And if you will just take any test point in the y axis, suppose 0 2, suppose if you will just consider, your equation is y dash equals to minus 2y, and then 2 into minus 2, this will just give you minus 4, which is less than 0, hence the slope is negative. So, it will again back to the steady state. So, if you just see this combined form of this vectors here. So, first if you just see here, so x axis and y axis we are just considering as the vectors here, and at the origin if you just see, since the eigenvector corresponding to y axis it is negative. So, y axis means it will just come towards the origin here, but if you just see the eigenvector for eigenvalue for x here, then it is just giving a positive eigenvalue. So, it will just move far away from the your steady state point. Then if combinedly if you will just take, then forcefully this y axis points it will come towards this origin here, but for this x axis this will just move outwards there itself. So, that is why you can just find that these arrows are coming towards the origin along the y axis, but it is just moving outwards in the x axis there. So, that is why it is just written as, if you will just consider any arbitrary point, suppose 1 1 here, x will try to throw away from y axis, will try to put back to the steady state. So, that is why it is just coming in this fashion here. This means that it is just forced towards the point origin along the y axis, and it just take away along the x axis there. So, if we will just consider for like matrix where this diagonal entries are existing, also all other entries are present there. So, like if you will just consider a matrix in the form of A equals to 0.50, 0, 0.75 and minus 1. Clearly, the eigenvalues are if you just see, this is a upper triangular matrix, hence the diagonal entries are these eigenvalues only. So, the eigenvalues are 0.50 and minus 1 here, and corresponding to this eigenvalue 0.50. So, the vector is coming as 1 0.5, and if you will just find this eigenvector corresponding to minus 1, it is just coming as a 0 1 here. Obviously, you can just find it in a direct form, a minus lambda I into V, this equals to 0. So, since lambda is a known to you, then directly you can just find the vector. And the solution of each of these dependent variables, you can just write it as x of t equals to, since first eigenvalue it is just giving you as minus 0.5 t plus C2 e to the power minus t here. So, this should be like 0.5 here, and second eigenvalue, since corresponding to this one, it will be minus 1 here. So, that is why it is like C2 e to the power minus t, and yt it can be written as a C3 e to the power minus 0.5 t plus C4 e to the power minus t. If you just find the relation among these c's by substituting this back into the system, then obviously you will have like x dash t if you just find here. So, this you will just written as 0.5 x t and y dash t it can be written as 0.75 x t minus y of t. So, after solving this we can just find it as like C1 by C3, this is nothing but 2, this is you can just find that this is nothing but the ratio of 2 eigenvectors there, but since vectors are not divisible we cannot write in that form. And similarly, if you just see here C2 by C4, this is 0, this is nothing but 0 by 1 itself, and you can just find that this eigenvector corresponding to minus 1 is this one 0 and 1, and eigenvector corresponding to 0.5 it is 1 and 0.5. So, these eigenvectors as I have told in the previous slide that they are not unique, and it can be multiplied by a constant value that it can be transformed, and this means that eigenvalue has more than one eigenvectors obtained by multiplying primary eigenvector by any constant value. So, if you just draw the phase diagram here, that is first draw the eigenvector for x equals to 0.5 y here, this means that 2x equals to y we can just say, sorry, yes 2x equals to y or y equals to 2x, so we can just write, and x equals to 0 and y axis all are like the lines presented here. So, if you just see here 0 0 point, if you just note it down here, then along the y axis since the eigenvalues are negative, so it is just approaching towards the point 0 0, and the eigenvalues if you just see for this x axis here, that is both are like 0.50 it is just present here. So, that is why these values are taken out from this point along the x axis, and if you will just analyze here the phase diagram of the system, then this kind of behavior it is called like saddle behavior, since at each of these corners. So, this comes from the horse saddle if you will just see this diagram here, and especially if you will just see that y axis, along the y axis these points are forcing towards the point 0 0, but it has been taken away since the x is representing the positive eigenvalues there. And if you will just go for like further analysis, so consider a system with 2 eigenvalues as negative values suppose here. So, if the 2 eigenvalues are negative here corresponding to this eigenvalues, you will have the eigenvectors suppose 1 0 and 0 1 suppose. Then x axis and y axis are the like eigenvectors it is just represented. So, then if you just see here that obviously minus 2 and minus 2 are the corresponding eigenvalues here, then along this axis you can just find that these values are approaching towards origin here, and any arbitrary point if you just choose like in the closer neighborhood of 0 0, then obviously that will also point towards this origin here. So, the phase diagram will look like this one here, since both these eigenvalues are negative, since along the x axis it will approach towards the 0 0 point, and along the y axis it will also approach towards the 0 0 point here. So, the phase diagram will have exactly opposite behavior if you just consider both these eigenvalues are positive here also. This means that if both these values are positive, so these values will go outwards from that, and you can just find that if any arbitrary point if you just choose, this point will move outward also from there. And if you just go for analysis of this complex eigenvalues, so first if you just consider eigenvalues like minus 1 plus or minus I2 here. So, since we are just considering 2 eigenvalues, this means that minus 1 plus iota 2 and minus 1 minus iota 2 here, and corresponding eigenvectors you can just find it as like suppose 2 2 plus or minus I minus 1 here respectively. If you will just analyze this system, then we can just represent the eigenvalues that is in the form of A plus or minus I beta here, and the corresponding eigenvectors especially we can just write it as like suppose P plus or minus I q, and especially we know that the solution is completely written in the form of x of t equals to e to the power a t c1 p sin b t plus c2 q cos b t. Already it is explained in the differential equations, second order differential equations, how we are just obtaining these solutions. And obviously C1 and C2 are constants, and if you just see here, the root is coming as in the form of a plus or minus I beta. So, that is why it is written as e to the power a t C1 sin p sin b t and C2 q cos b t here, and these eigenvectors which is associated as p and q here itself. And if you just consider like a equals to minus 1 suppose, then the nature of the phase diagram will be spiral. If you just see, it is just moving like this fashion here. Since this value is negative, so always exponentially it will just trace back towards the point 0 there. And if you just consider the term suppose x1 t as in the form of a p sin 2 t and plus q cos 2 t here, where p is represented as a 2 2 and q is represented as minus 1 1 here. At t equals to 0, if you just see, this will just represent, since sin 0 is 0 here and cos 0 is 1. So, that is why x1 t equals to q. So, we will start from the point like q equals to minus 1 1 here. So, minus 1 1 if you just start. At t equals to pi by 4, it will reach to the point p, that is 2 2 we will just reach. Again at t equals to pi by 2, we can just find this point x1 t equals to minus q, that is 1 minus 1 in this region, and at t equals to pi especially we can again reach to the minus 2 point. The same process will just repeat, and periodically we will just find that it will just go on decreasing, and finally it will just form a ellipse there. If you just consider like x of t equals to e to the power minus t x1 t suppose, since a equals to minus 1 if you just consider, and it is exponentially, it is just going on decreasing after starting from the point q at t equals to 0, it will go closer to the steady state, and it will just achieve this steady state spirally if you just see here, and if a would be positive, then it will just come outwards. So, it will just go away from the steady state. So, in this lecture we have introduced the phase diagram as it is required. So, phase diagram of one dimensional differential equation, then phase diagram of uncoupled linear system, then phase diagram for like a coupled system, then saddle behavior, then radial in behavior, then radial out behavior, elliptical behavior and spiral behavior. And the nature of a phase diagram not only depends on the eigenvalues, but it does depend on associated eigenvectors also. Sometimes if it is not determined based on these eigenvalues, we are just trying to find the associated eigenvectors, and plotting the eigenvectors especially we can just determine whether the system is representing a stable solution or an unstable solution. If you just consider like a case like if the diagonal entries are like minus 1.5, minus 0.5, and B is a system which represents minus 0.5 and minus 1.5. In both these cases the eigenvalues are negative, but the associated eigenvectors are different. Then we can have like eigenvectors in cases in a matrix A. If you just see here, the eigenvectors are 1 0 and 0 1 for minus 1.5 and minus 0.5, while in B the eigenvectors are interchanged. So, in that case also we can just use like these phase diagrams to find this like stability nature of this system. Thank you for listening this lecture.